Awesome. We should be in good shape. All right. Welcome back. You are on part 2 of 5. If this is the first time you are seeing this and you are watching this on the recorded version, you should probably go back and watch part 1 first. Other than that, you are on the right spot. So continuing on with our discussion on heat pump systems, and more specifically, different types of existing mechanical systems that you will run into and how those things work. And then how could you possibly convert that to a heat pump version of the similar type thing? So next up on our list, and last time was kind of a fundamentals, heat pump basics, how things work, economic balance points, thermal balance points, and things like that. Now we're going to specifically dig into packaged rooftop units. And then towards the end today, we'll dig into split systems, because a lot of what we cover on rooftops will also apply to split systems with some differences. So we'll talk about how these technologies are currently used, how they work, different ways that they currently heat, how we replace them normally, and what we want to do when we replace them with a heat pump type version of them. So let's dig into all of that. So packaged rooftop unit, as you might imagine, the word packaged implies that everything is packaged in one box, because it is. It is an air conditioner and a heater all in one box. For most of us, heater means it's got a gas furnace in it, although it could be electric heat as well, and it could be something else, but it's typically one of those two things, electric resistance heat or gas heat, all in one box. It has the same refrigeration cycle we talked about last week for cooling the air, so no difference in that regard. And it says rooftop unit, RTU, rooftop unit. So usually these are mounted on the roof, but it doesn't have to be on the roof. Sometimes we mount them on the ground, and then we duct them into the side of the building for various reasons. Maybe the roof is really, really sloped, or maybe the roof can't bear the weight of the rooftop because it's not designed that way. So we might mount them on the ground, but usually they're mounted on the roof to keep them out of the way, save parking space, have them be serviced on the roof where they don't interfere with any of the occupant usage of the ground, although it sucks from a service guy standpoint, but that's typically where they're at. If we do a heat pump version of these, which we'll talk about more later on, but everything's going to be the same in there, except we're going to add that reversing valve, just like we did last session. So that reversing valve, and there's a couple other little components from a control standpoint too, but from a mechanical moving parts perspective, the reversing valve was the only extra thing we add to the system when we designed it to become a heat pump version of the same system. And that allows us to do heating by extracting heat from the outdoors and putting it to the indoor air. If you don't know what I'm talking about, you definitely need to go watch session 1. So types of rooftops that you'll see out there, gas-fired packaged rooftop units are by far the most common thing you'd see in northern climates, but there is a pretty good amount of electric resistance versions of these. And then, as we said, there's heat pump versions, and then there's specialty versions, and that could be a wide range of things. In this particular example, we're showing one with energy recovery, but there's all kinds of other things that could be in there. About 54% of the United States is heated, I should say is cooled with packaged rooftop units. It's a little bit less for heating for various reasons, but from a cooling standpoint, 54% of the country for commercial buildings is being cooled with one of these units. So it is a lot of applications. We're going to focus on smaller stuff right now, which typically means 3 tons of cooling capacity up to like 20, 25, 30 tons of capacity. When you get bigger than that, you're into more customized type stuff, or at least semi-custom type stuff. So the types of components that we have, let me see if I can get the little laser pointer thing going. And by the way, I didn't mention it, but if you guys have questions as we're going, please just go ahead and ask them, type them in the question box there, and I'll do my best job of answering them. We actually do have one right now. Gary asks, did you send out certificates of attendance? I did not, but I bet Alberto probably did, or maybe Alberto is waiting till all 5 sessions are done and then they're going to send them out. That might be the case. So Alberto's on the call, so I'll let him answer that at some point here, and we'll figure that out. All right, components of the system. Because we don't have enough acronyms, there's another one down there, YAC. But I should just remove that, because nobody says that anymore, at least not since the 70s and 80s. So pretend that's not on there. Never mind that. Everyone just says rooftop unit. But components that we're going to have. So let's focus on the traditional outdoor stuff like you'd have on a regular system like at your house. There's a condenser fan that draws air through the coil and exhausts it up in this case. There's the condenser coil that runs the refrigerant through it. And then there's the compressor outside. Those three components are sitting in that unit for cooling purposes, just like they'd be sitting in your yard at home for cooling purposes. The other part of the cooling system at your house is the indoor piece, which is the evaporator coil, and then the indoor fan or blower. And those are also in this exact same box in this case. It's like there's this dividing line right here, and everything to the right of my mouse is what you'd have on an indoor unit at your home, and everything on the left is what you'd have on your outdoor unit, essentially. So condenser fan, compressor, condenser coil outside, evaporator coil and blower inside, as well as the gas-fired heat exchanger if you have a gas-fired unit, or an electric resistance coil if you have an electric heating unit. And the exhaust system for that is on the outside. So that's lines like the magical line between inside and outside, even though in this case, the entire thing is mounted outdoors. The other thing that's not shown on here and is not on every single unit, but is on a lot of them, is an economizer. That is a way to get free cooling in the wintertime. That is not always on a rooftop, but many times it will be. So we'll talk about that as things evolve here too. All right, so as mentioned, you normally mount these on the roof, and they would have what we call a vertical discharge, which means the supply air goes down into the building, and the return air comes back up through the building. All right, so there'll be an assembly on the roof. We typically call that the curb, where those connections can be made between the piece of equipment and the interior ductwork of the building. As I mentioned earlier, you could also mount it on the ground next to the building, in which case we'd have a horizontal discharge, where the supply air discharges horizontally out of the unit and goes through the wall of the building and then ducts throughout the building from there. It is also possible to have things like a horizontal discharge and a vertical return and weird combos like that. But usually it's all vertical or it's all horizontal, but there is opportunities in certain applications to mix them. So why do people use these packaged rooftop units? It's honestly because they're easy. Everything's in one box, right? It's already implied that it's going to be easy. It's pre-engineered. You only choose from a couple of different models. There's not a lot of choices, hence a lot of confusion. Everything's in one box, easy to do. Doesn't take up any indoor square footage. So as you probably know, architects don't like to give up square footage. If you put everything on the roof, hence more internal, leasable, usable space. And it also moves the sound from the unit more towards the outside of the building and less on the inside of the building. If you have larger areas, you can have multiple units serving that area. And if one of those goes down, you don't lose all of your capacity. For example, you might have a high school gymnasium. It might have 2 rooftops on it. If one of them goes down, you still have the other one running and you have half capacity. Or maybe it's like a big open store like a Menards or a Sam's Club or something like that. And they got 6 of these things on the roof. And if one of those goes down, they still have 5, 6 of their capacity. Obviously, if you have one small unit serving one little office area, then you don't have that redundancy. But on a bigger open spaces, you do. On some spaces, like say strip malls, for example, they like to use these because every individual tenant can have all their own stuff. They have their own electric meter, their own gas meter, their own packaged rooftop unit, and it just serves this Subway restaurant. And this one just serves the dry cleaner, and this one just serves the nail salon, et cetera, et cetera. As opposed to a larger commercial building where you have chillers and air handlers and shared systems, in which case you have to find a way to share the cost of operation of those. In this case, it's really clean. At least for the landlord, it's really clean. Everybody's got their own piece of equipment. It's your problem to pay for the gas and electric to that equipment. And then from a replacement standpoint, it's a little bit weird the past year or two because inventory of rooftops has been a little harder to come by than normal. But since I started in this industry in the 90s, even at the same company since the 90s, we've always had rooftops in stock. It's only been recently in the past year where it's been a struggle with lead times. But normally you'd have hundreds and hundreds of these things in stock. If someone has one that fails, they got a new one ready to put on the roof tomorrow and replace the old one. The disadvantages, the negatives to rooftops is you don't have a lot of flexibility. So there's only certain models and certain sizes and you get what you get. Oh, you need, 9.1 tons of cooling. Sorry, we don't have that. We have an 8.5 and we have a 10 ton. Which one would you like, right? You don't have as much flexibility. That's okay in most applications. All the service and maintenance is done outdoors, which doesn't sound bad until you realize it's super hot on a black tar roof, or it's raining or lightning or any of those things. You don't want any vibration from the unit to propagate its way through the roof, especially if you're putting this over a critical area. And then obviously everything being in the elements just makes it deteriorate a little bit faster than if you had half of the equipment inside, right? So common applications, like we said, strip malls, which are low-rise buildings, low-rise office buildings, sometimes schools, not always, but like maybe the office area at the school would have rooftops, whereas the classrooms might have unit ventilators or something like that. Fast food restaurants. It says residences on here, but that's not really common where you guys or even where I live. But sometimes down south, they'll use these package units in a residential application. The condenser coils might look differently. Just know that when you visually see them. From an inherent visual standpoint, if you see one of these V-coil designs, it's probably more efficient. I'm just saying that because it means that what happens on these rooftop units sitting on this curb right here, and when we go to replace this, we want something new that fits on the same curb, because then it's a really easy swap. Disconnect the gas and electric, pick the unit up, put the new unit down, connect the gas and electric. It's like a 2-hour project. If it doesn't line up with the old curb and the old ductwork, then it becomes a much more involved project, involves the roofing company and so forth. So they really want them to fit on the same spot. So over time, what manufacturers have done to get more efficient, one of the ways to do that is to get a larger condenser coil surface area on here relative to the size of compressor that you have. Well, you only have so much square footage on this guy. So going to one of these V-design type of condenser coils allows you to get more total surface square footage because you're cantilevering, you're hanging off the side of that curb with all of this extra over here. So that's one way that you might be able to get, more efficiency. It doesn't mean it's always the most efficient unit when you see this V design. It just means that there's a pretty good chance it's on that efficiency, higher efficiency side, at least at the year that it was built. As you guys have questions, type them in. I know we're covering a lot of fundamental stuff right now before we get to anything specific to heat pumps. So some of you may be well aware of this stuff. Some of you may have no idea what any of this is. So just ask. So this is the indoor, what we would call a blower section. It's the evaporator fan because it's the one that draws the air through the evaporator. Sometimes we call it a blower. Sometimes we call it a fan. We always call it something different in order to confuse you. Most of these are belt driven, but not all of them. What belt driven means is I have this motor here that's turning this, we'll call it a small pulley. And then there's a belt that turns a larger pulley. That is one way to get an electric motor to do more work than you otherwise would expect it to do. The other way is to take this motor and put it directly on this shaft. We'd call that a direct coupled system. It's coupled directly onto that shaft. I typically can't get as much torque that way and hence as much static pressure. That has changed with some of the newer fan designs, but a fan that's designed like this, a forward curve fan, or sometimes called a squirrel cage blower, a fan that's designed like this, it's almost always gonna be belt driven in order to get that extra torque and that extra capacity out of that guy. These pulleys can be changed to different sizes, and doing so would yield a different amount of airflow in the space. So this is the one that comes with it. When you put it in and install it, ideally, the person installing it would check how much airflow they're getting out of the system, compare it to what they wanted, and then change these to bigger or smaller pulleys to get what they wanted. Or sometimes they're adjustable, meaning that this gap, it can actually move in and out. And if you need more detail on this, it's a side discussion, but if you need more detail, I have all kinds of videos we've made on all that kind of stuff on how to adjust belts and fan tension, belt tension on fans and pulleys and stuff like that. But that pulley can expand in and out, which changes the length of it and hence the capacity. You can also slide it up and down on this sled. There's all kinds of ways to adjust capacity on it. But this guy is spinning. This back here, if you can see, is the evaporator coil. So it's sucking air through that coil and being cooled down by that coil. And then it's sucking it around into this fan. It's a centrifugal style fan where it's spinning around and throwing it to the outside of this housing. And when it gets to down here, there's nothing here. It's open straight to the bottom to the ductwork, and it throws the air downward that way. So this guy is discharging downward in this case. Whatever my clicker. And by the way, as you can probably see, I'm sitting in one of our training labs today. So I have rooftops back there as well as all kinds of other systems. If there's something you want to see while I'm here today towards the end, just tell me and I probably have it. And I'll probably do a really bad job of holding my laptop camera, but I'll give it a try. And we can point out anything on an existing unit that you want. As I mentioned, there's ways to do this now that are direct coupled that don't involve the belts, but still get a high amount of torque. So one of those is vane axial fans. And there's a whole blow up of it, which is a whole nother description in itself. But what that guy is doing is he's once again sucking air through this cooling coil, but in this case, it's sucking it down through this fan, through the heat exchanger into this space. And this particular fan design is a little bit unique in that regard. Only some manufacturers have something like this right now, at least on this size equipment. The nice thing about those vane axial fans is there are no belts. That's one less thing to break. There's no belt adjustment or belt tensioning. That's nice. Oops, little auto slide advance there. And they're typically significantly quieter and a little bit more efficient as well. So we've been using these for maybe like probably 4 years on packaged rooftops now. So it's becoming an established thing. All right, other stuff that's going to be involved in these units when you're looking at them visually on a roof, so you know what you're looking at. If you want to know how it's heated, if you see a gas line coming to it, and you know it's a gas line because not only is there a pipe coming to the unit, but there'll be some kind of gas regulator external to the unit. So when you see that pipe and that gas regulator, you know you have a gas-fired unit. That's how he's doing his heating. If there is no gas line to it, you definitely don't have a gas-fired rooftop. You probably have an electric resistance version, or it could be one with no heating. That's not common where we live. Or it could be one that's a heat pump, also not currently common. But there'll be a gas line to it, a gas regulator, and then there'll be a flue. So at a lot of places like your house, for example, you got a furnace or a boiler, and there's a flue coming off of that, right, where all the products of combustion can leave the home, and that flue goes all the way up to the second story of your house and then discharges out. We don't need that ductwork in this case because we're already outside. So the flue is literally like 6 inches long. It just has to push it a little bit away from the unit to get a little throw, and that's it. It doesn't involve anything else. So that guy's just when it's running heat, that guy is discharging flue gases right here on the side. In this case, there are a couple other things on here we might as well point out while we're here. There's a disconnect on here. This is an external disconnect. You could have a disconnect inside the unit. I don't really like that. I like it to be external. So when you go to change this unit in 15 years, you can just disconnect it from the disconnect and leave the disconnect sitting there for the next unit ready to go. But there's a disconnect here electrically, so you can shut it off while you're working on it. There's a gas valve you can shut off while you're working on it. This right here is an outside air intake hood. So it sucks fresh air in up the bottom of this guy. And it does that for a couple different reasons. One is for ventilation purposes. What's going on with my mouse? Hang on a second. Oh, there we go. I guess now, what the heck? Weird. All right, I guess we're going with a pen. All right, it sucks outside air in that way. And it also has a damper in here typically where it can open more or less, and it can open more when you want to get free cooling. What does that mean? That means the indoor space wants cooling, but it's mild outside. Maybe it's like 60 degrees outside or something like that. Well, if it's 60 degrees, why run my compressor in this unit? I'll just go ahead and open this damper more and just suck more cold air in, right? More means I get 3 hours instead of 1 hour. So suck more cool air in and free cool the space. But if it has this hood on here, it's very likely that it has an outside air economizer, which probably means it's a little more efficient than the average system as well. This is a exhaust fan here. We call it a power exhaust. There is a thing called a barometric exhaust, which just like relieves the air like naturally via barometric pressure. This one's a power exhaust where it uses a fan to suck the air out. So as I bring more and more outside air in, the building would become pressurized. In order to relieve that pressure, there's this fan that discharges air out from the building as well. So as I suck more in, I have to send more out. From a gas heating standpoint, there are 2 types of heat exchangers that you typically would have on a gas-fired rooftop. You have an aluminum heat exchanger, and then you have a stainless steel one. As you might guess, the stainless steel one costs more, but it also lasts longer. In most applications, as you might guess, get an aluminum heat exchanger because it costs less. And first cost is a very high focus point of packaged rooftops. It is definitely a commodity type thing, and every kind of building uses it. And it's typically not the super high-end buildings, right? It's not like your universities or something like that. So it's regular buildings. So first cost is important. So a lot of them get aluminum. Stainless steel would be if you have an owner that is going to be there a long time, like they're an established company, they've been there for 15 years, they know they're going to be there another 15 years, they might ask for better things, like a stainless steel heat exchanger. Or if you have an application that has a lot of outside air all the time, you might be required by the manufacturer to put a stainless steel heat exchanger in because it's condensing on there with the cold air. And then there's an exhaust fan on there. We call that an inducer fan because it sucks air through the heat exchanger. This is where that little hood went, where it blows the exhaust out. And then the motor is physically inside the cabinet. Like I said, you need a stainless steel heat exchanger if you're going to be experiencing colder air. This is air entering into the heat exchanger. So you have return air and outside air mixing and then going into this heat exchanger. So maybe if you have a lot of outside air, say like 30% outside air, and it's, Boston, so it's 5 degrees or something in the winter, that's a lot of outside air. I might have to do this stainless steel version. If you have electric resistance heat, then obviously you will not see a gas line to the unit, right? And you'll see regular stuff like electrical wiring, but that doesn't mean there's electric heat. It could be a cooling only or a heat pump. It's probably not a heat pump, and it's not likely to be cooling only either. So it probably does have electric heat, but to be sure, when you open up that unit, you will see tons of fuses in there, right? Instead of just a couple fuses for the fan and the compressor, you'll see fuses for all these individual heaters. And then if you look, this is the fan blowing downward. You'll see that electric heater right here. So this right here I circled is this right here, right? If it's electric heat, from last discussion from the module 1 that we should definitely be looking at a heat pump. They don't have a gas line, obviously. So it doesn't matter what the cost of gas is. They don't have a gas line there. So now their choices are heating it with electric, which is 100% efficient, or heating it with a heat pump, which is a couple 100% efficient. You should definitely get the heat pump. And you'll still have electric heater as well, because we need that auxiliary heat sometimes. But if you find this electric heat in there, it's an immediate point that you should be discussing with the building owner / operator that that a heat pump upgrade is something they should look at, and probably look at it relatively soon, even if it's not an old unit, because a heat pump replacing an all-electric system can have a really quick payback. Whereas a heat pump replacing a gas system, probably not a quick payback, and in many cases, not even a payback, because gas can be pretty cheap, depending on what's going on. But electric heat, definitely a heat pump option. All right, there's this chart, and I can send this to you guys. And by me saying I can't send it, I mean I'm going to write down a note and I'm going to send it, because otherwise I'm going to forget that I just said to send that. Repair replace chart. And if you've been to any of our classes there locally, where I've come and done them with you guys on rooftops in the Boston market, we've used these charts before. I'm not going to go through the whole chart right now in the interest of time, but just know that this is available to you. It's a little scorecard. You have to do the scorecard with the person making the decision. Filling it out and handing it to them does nothing. You have to sit there and do it with them. And basically you go through and you rank things, right? So if they have a gas-fired heating rooftop, you're on this column. And I broke the chart into 2 pieces so it fit on the screen today, but it's normally just one 8.5 by 11 page. And you're like, oh, you got a 15-year-old unit, boom, 10 negative points. Points mean that you should probably replace this thing. How much does it cost to repair whatever it is I'm there for? Because chances you getting called when there's something broke is low. So you're there because something's broke. Like, oh yeah, you need this new motor or whatever, and that motor costs $900. Okay, boom, I'm over here in the $900 range. That's 5 more negative points, right? Or it's more expensive. Obviously, the more expensive the repair, the more likely you'd want to be to replace the whole unit. The less expensive the repair, maybe not. So you add up all these different things. How old's the unit? How much to repair it? How efficient is it happen to be? Is it using obsoleted refrigerants? And then this is the best one. You ask them to rate their equipment. It doesn't say on here what good, average, fair, and poor means. It doesn't at all. But everybody knows if they have good, average, fair, or poor, because it's relative to them. Like if I asked any of you, which is hard to do on a webinar, but like, hey, what kind of car do you have? Is it in good condition? Is it average? Is it really crappy? You know what it is. You'll immediately, all of you, if we were in a live room right now, you'd all blurt out what you have, right? Oh yeah, my car's average. Oh, my car, it's crap. I need a new one. Like, you know already in your head. And that's the biggest thing. If they think they have a crappy air conditioning system, fine, 30 negative points. If they love this thing and it's been hardly a problem ever and they've had no pain, like it's never broken before, yeah, it's in good condition, bro. It's like nothing wrong with that thing. Less negative points. It's their opinion on what it is. And then how long they're going to stay there. And then you add it up and it says if you should repair it, you should replace it in its entirety, or you're somewhere in the middle. I'm going to tell you, most of the answers come up in the middle. And that's okay. And the chart is designed that way on purpose, because I don't really care what the answer is. I mean, the owner does, but I don't really care what the answer is. I just want them to go through the process of thinking about all these things, so they are more educated on if they should think about repairing it or replacing it. And the back side of the sheet has all these red flag questions. You ask them each of these questions, right? If you ask them how it works, they're like, well, other than today when the motor broke, everything's been fine. What the hell does been fine mean? Been fine means it wasn't 100 degrees in here and it wasn't 30 degrees in here. It's been fine, but you have to be really probing with the questions. Same thing happens at residential houses. I'm like, how's your system work? They're like, yeah, it's fine. If I ask them something else, like, what room in the house is the hottest? They're like, oh, dude, my kid's room above the garage, it's like roasting up there. You just said it was fine a minute ago. And now all of a sudden you have this horrible room. You have to ask all these pinpointed questions in order to get them to actually give you some info, because people are just used to things sucking. So they're like, it's fine. So you got to ask them these detailed questions, which I'm not going to go through today. But once again, it's just to get them talking about these things. And then you could try to solve them when you give them the options. And you should be prepared to solve any of these things. If not, don't ask these questions, right? Delete them off the sheet. And if you don't know how to solve it, don't ask them, or find someone that does, I guess. All right, back to the rooftop itself. All right, so rooftops physically sit on this thing I mentioned called a curb. That curb is connected to the roof membrane assembly. So the roofer puts this in, not the HVAC guy. The HVAC guy provides the curb, gets it up on the roof, and then the roofer connects it to the roofing material. And then the HVAC guy and usually there's a piece of sheet metal covering it until it's time to install the equipment. And then they take the sheet metal off and they put the rooftop unit on it. Right, so that's how the building is built. You order a curb that's specific to this rooftop. You order the curb 3 months before you need the rooftop unit, and have the roofer put it in and cap it off and have it sitting there for when the equipment comes later on. If you want to change to a different piece of equipment, the ductwork connections don't always line up. In fact, they seldom line up, which means you need to take the curb out and put a new curb in, which means you got to get the roofer involved and possibly cut the hole bigger or make it smaller, whatever you got to do. So ideally, you'd like a new rooftop to fit where the old one fit, which means you're going to try to find one from the same manufacturer that has the same dimensional openings, or you're going to get a thing called a curb adapter, which adapts you. It's a piece you stick in between that adapts you from this curb to the new unit that you're going to buy, because it doesn't line up exactly. I'll show you some pictures of it. So you might get a curb adapter. You can usually do that, but not always, but usually you could. So when you have one of these adapters, you lift the old unit off the roof with a crane, obviously. Unless it's really small, then maybe you can manually lift it, which we do sometimes. But usually there's a crane involved. Lift the old unit off, especially for one that size. You prepare the old curb, which means you clean off all the debris. There's probably adhesive and tape and stuff like that on there. You scrape all that crap off, so it's just the bare metal sticking out. And then usually you put a gasketing material down, and you'll set this curb adapter on top of it. The bottom of the curb adapter has to have duct connections that line up with the old curb. And the top of the adapter has to have duct connections that line up with the new rooftop unit. That's basically his job, is to shift this duct flow over X amount of inches to the side or whatever it needs to be to make it line up. And then you set the new unit on that. So this is my old curb down here in black. The silver thing in this case is my adapter. And then this is my rooftop unit on top of it. This is really common to do. In order to do this, when you're replacing it, what normally happens is that whoever you're getting bids from the rooftop, they go to the supplier of that rooftop unit and they say, hey, I'm taking off a whatever. I'm taking off a Lennox model, XYZ, whatever it is. And I'm putting on a Carrier or whatever model number. As you can tell, I work at a Carrier distributor, so it's always replaced with a Carrier. I'm putting on a Carrier ABC. And then they can go look up the dimensions of these two things and say, oh, yeah, those things line up. Or no, dude, that's not even close. We need this adapter, right? So you got to figure out what adapter fits between them. This is a corny, cheesy little animation to kind of show what happens, but lift up the unit. There's the old curb and its duct connection points. Set this curb adapter on, and you can see the new adapter doesn't. The bottom is going to line up with the old curb. The top's going to line up with the new unit, and then set the new unit on it. In this particular example is because we were going from a certain size unit, maybe a 10-ton unit, down to an 8-ton unit or something like that. That's why it's a little physically smaller. Usually they're not getting smaller, but sometimes they do. We mentioned also too, like when you're doing, when you're in this scenario here, and I said you need to know the old unit and the new unit. Sometimes you'll go to a job site and it already has an adapter on there, right? So the building was built, there was a curb and a rooftop. Let's just say it was an old Carrier unit that was on the unit. And then 20 years later, that thing got replaced with a Lennox unit and they put a curb adapter on it. And now 20 years later, again, you're coming in and now you're like, oh, I got to adapt this this carrier to this Lennox. That's not what you want to do, because now you have an adapter stacked on top of another adapter. And as you can see on that other drawing, those adapters are going to have some pressure penalties associated with them. And you're going to have a real hard time moving air through an adapter through another adapter. So you don't ever put an adapter on top of an adapter. If that scenario happened, like I just described, hey, I got this carrier unit, 20 years later, I replaced it with this Lennox and an adapter. Now it's 20 years later again. What I want to do is figure out what unit was underneath that Lennox originally. And I want to get an adapter to that unit and skip this thing in the middle that I'm going to throw in the trash anyway. Right. So that becomes a little more challenging. Sometimes you can get that off the old blueprints, but usually in those cases, you need to field measure the curb and give the dimensions of what's underneath the adapter to the supplier so they can figure out what to put in there now. All right, let's see if there's any questions while we're here at the natural breaking point. Gary said, is this chart used for residential split systems? I am guessing that Gary is talking about that repair, replace comparison chart, little scorecard thing. And yeah, we use the exact same chart on residential systems and light commercial like we were showing here. You could actually use it for anything. We've taken it and just, you change some of the questions on there and adapt it to whatever you want. And once again, like I said, it doesn't really matter what the answer comes out to in the mathematical thing. It's just that you want the person making the decision to go through the process of thinking of all of those things. So make sure you don't forget anything. All right, I mentioned last week we showed some calculators, and hopefully you got the links to the calculators that I had shown you guys. There are residential ones in that example. This is a commercial one. It's very similar. This is a software tool called Invest. This one's a carrier tool because, like I said, I work at a carrier distributor during the day, so all my stuff is carrier. I can certainly give this to you. It's not as easy as going to a website. The other one, this is something you have to install on a Windows desktop. And there's like 3 or 4 pieces of software you install on top of the others to make it work, because it's actually just one little piece of a much larger suite of software. So you have to install all the other software so you get the engine that does the calculations. If you're familiar with a software tool called Hourly Analysis Program, it's used for load estimating and robust energy modeling and stuff like that. This tool uses that engine, but what it does is it puts a bunch of assumptions in. Instead of making you energy model the whole building, which might take hours or days, you put a bunch of assumptions in, and this can do it basically in 5 minutes. It doesn't do the most awesomest job of giving you the exact operating costs you're going to have. What it does do a great job is showing you the difference between operating cost on choice A versus choice B. And that's really what I want in this scenario. I don't really care if it costs $1,000 to operate the old unit and $1,200 to operate, that's a bad example, $1,000 to operate the old unit and $800 to operate the new unit. I just want to know that it's going to save $200 in operating costs from whatever I'm paying now, right? So I'm really concerned about the delta in this case. So the assumption thing is okay, not great, but okay. But it takes 5 minutes and not all day. So there's that trade-off. All right. So in this software tool, what you do is you obviously name it whatever you want to name it, right? And then you put in your weather data. You pick it from a drop down. It doesn't have every possible city, but it has all the major cities, right? So 3 or 4 cities per state. Although your guys' state is geographically small, so it may only have a couple. But you put in that to get so it knows the weather data, and then you put in how much cooling capacity this building needs and what kind of building it is, right? An office versus a school versus a restaurant all have pretty varying needs and varying operating hours. You can't go in here and tell it what the operating hours are. Like, if you want to start getting detailed like that, you need an energy modeling tool. This is just a quickie tool. So it's making giant assumptions for you to make it fast. And then you put in your energy data. You can either take the EIA data, which is kind of like the national database average, or you can choose user defined, and then you can type in whatever you want for electric and gas costs, right? In this case, I took the EIA data, and I did this a couple of years ago. So it's probably a little bit more for electric now than it was. That's how you put that information in. And then what's going to happen is you are going to put in choice A and choice B on here. And you can actually change that to have more than 2 choices. You can put in, 4, 5, 6 choices on here. The current example that I'm showing you on here is what would be considered a legal code minimum unit, and then a heat pump unit. So this is not an example of my existing unit and then a heat pump unit. It's my replacement. I'm going to replace it with this thing. Like, I'm taking this old 20-year unit off. I'm going to put this exact model on in its spot. Or choice B is I'm going to put the heat pump version of that model on in its spot. which one do you want to do, right? So in this case, I'm picking them from the drop down by model number. There's also ability to put in a user defined where I say, I got this weird thing, I don't even know what it is. And then I have to type in all of its old AHRI data from 20 years ago. But if it's one of the ones in the drop down, which is, I think, Train, Carrier, Lennox, and York, I believe, are in there as a default, I already know that information on there. And I could tell it if I had any accessories. In this case, I'm telling it I want to put in a brand new unit at this efficiency level. I want to get a 2-speed fan, which is required by code in your state right now for this size unit. And I want to get an economizer, also required by code. And on the heat pump version, I'm also going to do those things because they're required by code, right? But I'm getting a heat pump version. One thing you will notice is that the fan horsepower is different on here. These are the same unit in the same cabinet, same compressor, same cooling coil, but I have lower fan horsepower on the heat pump. That is normal. Gas-fired equipment requires a fan that can do more air movement. I shouldn't say more, but it requires more energy to move the same amount of air because I have to shove the air through the evaporator coil. Then I have to shove the air through the gas-fired heat exchanger coil. So it takes more horsepower to do that. So I'm going to have less horsepower here. So I'm going to save fan energy by doing a heat pump versus a gas heat system. And my efficiency also improved for the same reason. The efficiency level includes the fan energy. So that one for the cooling side also improved. And then I'm going to get something like this. Let me turn off this laser thing and move this other zoom thing out of my way. All right. So in this case, it's saying, hey, if you put that unit in, it's going to cost you this amount of money to operate it over the course of the next 5 years, $600. But if I put the other one in, it's going to cost me this much. So it's going to save me $133 in this case. You can argue about whether these are accurate or not, right? And that depends on what your fuel costs are and if your load is actually what you thought it was. But I just want to know what the delta is here. So I'm going to save $280 on fan energy by putting in the heat pump versus the gas heat one. The cooling energy, it's pretty minimal, $2 a year. That's basically zero, right? It's going to put more electricity, more of my heating bill is going to go on my electric tab, but it's going to come off of my gas tab. And in this case, it's going to save me $130 a year. It's not a lot of money, not a big difference. If I go back and I change these fuel costs and say my gas costs less, then obviously that changes the math and all of a sudden the heat pump's not a good deal. Or if my gas costs more, heat pump becomes a better deal. Same with electric. Electric prices go down, heat pump's a better idea. Electric prices go up, gas furnace is a better idea, right? Just like we talked about last week. This example, same software tool, same size building, same costs of operation and all that. But now instead of I'm comparing a gas to a heat pump, I'm comparing an all-electric system, electric resistance heat, to a heat pump version. And everything else I picked is exactly the same here, right? And in this case, it's going to save a lot more money. Because as we said last week, heating with electricity for electric resistance is probably the most costly way you could heat a building in most towns. So getting the electric heat replaced with a heat pump version will do a phenomenal job for saving me energy. All right. Pending questions. Let me check this question box thing. Don't see any at the moment. If anybody has any questions, type them in the question box, and I'll do my best to answer them. But I think we got them all out. All right, I got them all, I think. So I can hide the question box, hide this little bar, and now we're back. All right, a DX split system. So when we use the term DX, that means direct expansion. Almost everything you're familiar with is a direct expansion system. So what that means is the refrigerant expands inside the evaporator coil that's in the airstream. The things that would not be a direct expansion system, like a chiller, right? The expansion of the refrigerant is happening over at the chiller. It's not happening in my airstream. I have chilled water in my airstream cooling down my air. So the things that you're familiar with, residential split system at your home, a ductless mini split, packaged rooftop unit. Those are all DX split systems. So I could have just said split system and left the DX word off, and it's kind of implied. But for whatever reason, the vernacular is that people call this a DX split system, right? So you're going to have two major pieces, an air handler and a condensing unit, just like we had in the examples last week when we talked about a house, we'll say. It's just things are going to get bigger. Instead of being a little 3-ton unit, it's going to be bigger. It's going to be 30 tons, 20 tons, 48 tons, whatever it is. So an outdoor condensing unit and an indoor air handler. The outdoor condensing unit has the condenser fan, the condenser coil, and the compressor all out there. The indoor unit has the evaporator coil and the main blower on it, and then possibly also another heating source, electric heat, gas-fired furnace, something of that nature. If I want to make this into a heat pump version, I need to get an outdoor unit that has a reversing valve in it, just like we talked about on all the other types of systems. I need that reversing valve. That would make it a heat pump system. There are other components, slightly different controls for defrost and things like that, an accumulator inside, but the only moving part really is that reversing valve, right? And then I can make this into a heat pump version of that. So a normal type of system, I'd have the condensing unit sitting outside and the air handler would be inside. In this example, we're showing one in the ceiling. It doesn't have to be in the ceiling. It could be in an entire mechanical room. It could be in a closet. It could be vertically mounted. It could be horizontally mounted. It could be under the flooring system. It could be in an attic, ducted downward in. It could be in a basement, ducted upward. There's lots of options for that. And these guys can have some level of distance between them. So this doesn't have to be like 10 feet away. Depending on the model of this unit, it could be 10 feet away, right? It could be 100 feet away. It could be 200 feet away. So it allows you some flexibility on where this thing locates. From a service standpoint, some of your service is done on the roof, or this could be on the ground next to the building too, right? Some of it's done outside, and some of your service is done inside the building. We have to be a little bit smart on where you locate the indoor unit. Like in this case, it's in the ceiling. There is going to be a condensate pan and there is going to be a condensate drain, just like your system at home has, but now it's above the ceiling. So it's important to know what's going to be located underneath it. Do I want to do this in a server room with a bunch of expensive servers? No, I don't want water above electrical servers. Pass. That's a hard no, right? Do I want to put this above the bathroom? Yeah, maybe, because like if it drips water in the bathroom, that's like the least concerning place for it to drip water, right? I got a tile floor. I can kind of deal with it a little bit better. So what's underneath it does make a difference on where you locate it. But sometimes you don't get a lot of choices based on what the architect or the building owner will give you to work with. The outdoor condensing unit can look like lots of different things. And by the way, we only call it a condensing unit if it's an AC version. Once it becomes a heat pump version, which looks exactly the same as these things, we no longer call it a condensing unit because that coil outside is a condenser coil. And then in the heating mode, it's an evaporator coil. So calling it a condensing unit becomes weird. There's also the term condensing unit and condenser, and some people use those interchangeably. Condensing unit, properly speaking, would imply that it has a condenser coil, a condenser fan, and a compressor. A condenser would just be the condenser coil and the condenser fan and no compressor. The compressor would be located inside the building. So that would be a significantly different type of setup, but it might look similar. It would look something like this one right here in the middle, except you can't see the compressors in the back here, which is fine because now it looks like a condenser instead of a condensing unit. So condensing unit means it has the compressor also in it outside. Condenser means the compressor is inside. Where will you see a condenser? The most common application would be like a supermarket. If you go in a supermarket, there's usually in the back room, there's usually a mezzanine with tons of compressors there. And those compressors are all piped to all the freezers and refrigerated cases. And then the condenser is out on the roof. For some reason, that industry has evolved that the compressors are in a mezzanine and the condensers are up on the roof. I don't know why it evolved that way. It just did. Maybe there's a technical reason. I don't do supermarket work, so I don't know. But that would be an example of it. Another one would be, not always, but sometimes, computer room units. So you got an old computer room in a building where they have like that raised floor and they pressurize the floor with air. And then there's like a Liebert unit in there. That Liebert unit might have a compressor in it. And then there's a condenser outside. That's a fan and a coil only and no compressor outside. What we're going to do is normal stuff. So regular comfort conditioning and comfort cooling for regular buildings. So it's almost always going to be a condensing unit. Someone might say condenser. That's fine. Don't correct them. Don't be that guy. Just roll with it. But they look at like all different kinds of things. Anything from like the residential one that you have in your house to a mini split. So these more commercial ones, these are probably all like 12, 15, 20 ton units over here. This one over here is a larger unit. It's probably like 30, 40, 50, 60 tons. And it's older. I know it's older because it has reciprocating compressors on the bottom, but there's obviously newer versions of that as well. The indoor unit will be an air handler. And similarly, there's all kinds of looks to what that would visually look like. So it could be something really big like this one over here, right? It could be small ones. It could be horizontal airflow pass. It could be vertical, where this guy's sucking air in here, discharging it up there. This guy's sucking air in the back, discharging it on the top. This guy's sucking air in the side, discharging it out the top. There's all kinds of look, and there's dozens of other ways these could look as well. These are just some sample pictures that I grabbed. So there's all kinds of different versions of what the indoor piece of equipment could look like. But if you see one of these somewhere in the building, there has to be one or multiples of these doing the air handling side of the equation. We call it an air handler because it handles the air. We're not creative with the naming, but that means it has a fan and a cooling coil and possibly other stuff, heating system, humidifier, filtration, all those kinds of things. So where does this fit into the overall piece of the puzzle? So on this particular building here, I have this space. This is just one room, but obviously I'd have lots of rooms in the building. This is one example room. I am going to have air leave the room through the return duct. It's going to get sucked into the air handling system. Everything in this circle over here is basically our air handler. It could all be one giant box like this guy was, everything in one box, or it could be split pieces. There could be this supply side. There could be a separate external return fan, this damper over here at the exterior wall, or all of it can be in one box. Either way, we'd call it the air handling system. Whether it's in one box or distributed boxes for space reasons. It sucks return air back. Some of that air gets brought back to the supply side of the air handler and mixes with outside air. So we mix outside fresh air and return air together. And then we take that into your heating and cooling coils, into the supply fan, and bring it into the space. This cooling coil right here could be fed with a chiller, like it is in this case. A chiller makes cold water and sends it over here. Or it could be one of those split condensing units we talked about over here. If it's a chiller, that's going to be a different solution for heat pump versions, and we'll talk about that on Module 5. So if it's going to be a DX system, meaning it's got one of these units on the roof, piped over to this guy, right? That's what we're talking about today, and what we can do to replace that with a heat pump version. So knowing if it's chilled water or not chilled water is going to make a decision on what type of path you go down in terms of recommending solutions. If it's chilled water air handler, your cooling coil is going to be different. Everything else could be exactly the same, honestly. Everything else could be the same. Drain pan, fan, heating system, dampers, all of it could be identical. The cooling coil is the only thing where you'll be able to tell if it's chilled water or not chilled water. So when you open the door on the air handler to the cooling coil, you will either see two headers like this, which means, let's just say, for example, chilled water comes in here at like, say, 44 degrees. It runs down this coil to the far end and goes to a U-bend, comes back, down, back, until it gets to the last row, and it fills up this return header. At that point, it's 56 degrees because warm air is blowing across this coil and giving its heat to the water. So the 44-degree water ends up cooling down to 56. We send it back to the chiller. If it is a DX system, direct expansion, there'll be a condenser on the roof, but you may not have been to the roof yet. You're just in the air handler room. And when you open up the door to the cooling coil, it will not look like this with a supply and return header. Instead, it'll look like this. It'll have all these distribution tubes. So the refrigerant will come into these distribution tubes, kind of like spider webbish almost, and has all these little tiny copper lines that go. And then those guys send refrigerant up and down, up and down, and up and down until they get back to these, in this case, 2 return headers. So if you see this spaghetti looking set of copper piping here, it's a DX system, which means we can get a heat pump version for that. And if it's this kind of distribution, and when you open the door to the air handler, it's a chilled water system. And we're not talking about today. That's Module 5. Any questions on those? Does that make sense? It's a quiet group today. If anybody has anything, man, blurt it out. I'm here to answer questions. Okay. Be careful, because when you open up this and you see this, it might not be a cooling coil. It might be the hot water or steam coil, because they look the same, right? The cooling coil will have a condensate catch drain pan on the bottom over here. The heating coil won't. So you might have this for heating, right? And then just upstream of that guy, you may have this for cooling. So you got to make sure you're on the cooling coil, because the heating hot water coil looks exactly like a chill water coil. So once I know my type of cooling system, now my next question is, well, what kind of heating system do I have? Because that's going to make a difference on what I can offer as well. So if it's a hot water boiler or a steam boiler, you'll have a coil like this. Once again, air is going to blow through here. I'm going to send it, for example, 180-degree supply boiler water. It's going to fill up this header. That's going to go up and down the coil. These U-bends on this side have U-bends on the other side that look exactly the same. Come back on row 2 and 3, 4, serpentine back and forth until it comes to this return header. And then my boiler water goes back at 160 to the boiler to be heated up again back to 180 because I've sent 20 degrees worth of heat into that water. So I'm looking for that. Now, just looking at it won't necessarily tell me if it's a hot water or a steam coil. I'm going to have to look at other stuff like, is there a trap on it, or go look at the boiler itself, right? But in either case, if it's hot water or steam, from a heat pump replacement standpoint, that answer is going to send me down one path. If they have hot water or steam, my heat pump decision is going to be the same. If they have electric resistance heating, I'll have a heater like this, like we saw on all the other stuff, and that's going to be a different answer for heat pump. Once again, based on last week, anytime someone has electric resistance heating, they should always be getting a heat pump, no matter where they live and no matter what their electric price is. It's always a heat pump when they replace it. It should never be anything else if they have an all-electric system. If they got a gas boiler or steam boiler, there might be different math, and they may or may not benefit from a heat pump. But all electric, no-brainer. Definitely do a heat pump. All right, so let's say I have a DX cooling split system, right? Or even a rooftop unit, and I've made the choice of replacing it with a heat pump. I'm going to do that. I'm pulling the trigger. I'm getting the heat pump for whatever reasons, either the economics, or they said they wanted to get rid of fossil fuels, whatever the reason. I'm going down the heat pump path. So things that I might have to do other than just changing it out. If I'm going to change out my exact system for a brand new exact system, it's pretty easy, right? Turn the gas off, disconnect the electric, remove the rooftop unit, put the new one down. Maybe I do a curb adapter, maybe not, depends on the situation. Put it down, reconnect my stuff, I'm up and running, okay? If I'm going to go to a heat pump, it may not be quite that easy depending on what I have. I may need to change the electrical high voltage supply to the unit. I might not, but I might need to do that. It just depends, right? So let's do a couple examples of that discussion. Let's say I have electric resistance heating on a split system air handler, meaning one part's inside, one part's outside. There's a pretty good chance I don't have to upgrade the electrical outside. Probably not, right? I already have all electric I need inside for electric heater. The outside, the heat pump will probably run on the same gauge wire that I had the AC on. It's probably not going to need this, right? But if it was a packaged rooftop unit with gas, I'm going to get rid of the gas and replace it with a heat pump that has electric auxiliary resistance heat. Now I probably am going to need an electrical upgrade because the heat pump's probably fine. Instead of running the air conditioner, I'm running a heat pump. No big deal, right? But now I got this electric heater that I didn't have before. So now I need power for that. So I will probably need an electrical upgrade from switching, like it says in the notes here, from a gas-fired system or even in a hydronic or steam system, hot water or steam system, to an all-electric system. I'm probably going to need more electrical power. And by probably, I mean I am, for sure. The thermostat wiring is the other thing that might have to change, and usually it will. All right, so I know most of you guys have not installed thermostats, but let's see if we can do a few basics on here just to get everybody on the same page. So on a normal thermostat, and this is showing a thermostat right here. This happens to be an Ecobee one, but all of them work in a similar fashion. This is my thermostat, all that wiring. These wires are going through the walls and so forth. This is my air handler or furnace sitting in my ceiling, closet, basement, whatever. And then this is my air conditioning / condensing unit sitting outdoors. So I have thermostat wire connecting those three things. Your house is the same way. Your thermostat wires back to your furnace or air handler, and your furnace or air handler wires to your condensing unit or heat pump outside, right? How do I clear this? There we go. All right. So we got all those pieces there. So what those guys do, each of these wires has a job. So the transformer is usually located in the air handler. The transformer takes the high voltage power, 120 or 240, whatever it is, and drops it down to 24 volts because almost all thermostats and the control boards they're tied to work on 24 volts. So the furnace typically is the owner of that, or rooftop unit, or air handler, whatever you have. And that guy provides power to other things. Specifically, in this case, he's going to power up this thermostat. So on the C wire, that means common, and the R wire, that means red, colored, doesn't have to be, but typically means red, and that's the hot. So R and C provide power to the thermostat, those two wires. The G wire, usually green, that's why it's G. His job is to turn the fan on. The Y wire, usually yellow, his job is to turn the cooling on. And the W wire, usually white, his job is to turn heating on. And if you have two-stage equipment, you might have another Y and another W on there. So those guys all 1, 2, 3, 4, 5 wires go down to the furnace or the air handler, whatever you got. And then 2 of those wires piggyback outside. And if you have two-stage, then another one as well to your air conditioning unit. When I have a heat pump, it's going to require more wires. This is where the change would come in. When you're replacing an air conditioner with a heat pump, you probably have to run new thermostat wire because you probably don't have enough wires, right? Maybe you're lucky and it's the one job where somebody pulled 10 conductor wire because that's what they had on their truck that day, but they probably did. They probably pulled exactly 5 wires. So on a heat pump, you still have R and C for power. You still have G for fan. You still have Y, but instead of Y being cooling, Y is now compressor. You still have W for your auxiliary heating situation. And then you have an extra wire from the thermostat over to the air handler or furnace. That is labeled as O/B, typically because it's either orange or black. And the orange and black meant different things back in the day. But this is my reversing valve wire. The thermostat has to tell the reversing valve to switch between heating and or cooling. So when it turns on Y, that Y gets piggybacked to the outdoor unit, Y1 in this case, and that would turn on the compressor. Do I want the compressor to run with the reversing valve ready for cooling, or do I want the compressor to run with the reversing valve ready for heating? On the straight cooling system, I didn't have to worry about that because it didn't have a reversing valve. Now I got a reversing valve, and the thermostat is the one whose job is to tell it that. It means I need an extra wire from the thermostat to the air handler, and it means I need an extra wire from the air handler to piggyback out to the condensing unit outside, or excuse me, the heat pump outside. So now I have Y, C, and O/B going outside, 3 wires instead of just the 2 over here, right? Additionally, in most situations, I'm also going to need to run the hot R outside for transformer power and the W also. What's going to happen in those cases is W and R at the heat pump will connect to each other. They'll close electrical contact. That'll energize the indoor heater, which can mean electric heater or gas-fired heater, whatever you have. It's going to do that in place of the thermostat. The thermostat can still turn on the, let's say it's electric heat, turn on the electric resistance heater when the heat pump can't keep up. But also the heat pump could turn on an electric heater, specifically when the heat pump goes into defrost mode. Remember from last week, when it goes into defrost mode, it really runs cooling in order to thaw the coil outside. That's great. It thawed my coil. Perfect. But it also means I'm blowing cold air inside for a building that wants heat. Not perfect. So when this heat pump goes into defrost mode to thaw its coil, it tells the indoor electric resistance heater, hey, dude, I'm going into defrost. You need to kick on so these people don't get a bunch of cold air blowing at them. We're a team here, man. You got to help me out. So I need that extra wire. So on a heat pump upgrade from a straight AC, I will need at least 1 extra wire for the reversing valve from the thermostat to the indoor unit. And then from the indoor unit to the outdoor unit, I will need 5 wires instead of 2. So I'm going to need to pull additional wire. If you don't want to pull additional wire, that is okay. There's options around that. Specifically, you can get one of these kits. This is a manufacturer called Fastat. I'm not bragging about specific manufacturers. They're just the only ones I know that have this exact thing. There's lots of manufacturers that have things called add-a-wire kits, and those are cool, and we've used them for decades. They don't work on heat pumps because they only add 1 wire, and I need to add a bunch of wires. So what ends up happening with one of these, I'm just going to use, let's use this one as an example. This one's a less expensive, simpler version. This one's the more complicated one. If you understand the more complicated one, you understand both. By the way, the 7,000 for this brand does more stuff than the 9,000. And from a model number standpoint, that bothers me. So just know that. Here's my thermostat up here. Here's my indoor unit, air handler, or furnace, whatever I got. And then here's my outdoor heat pump over here. So you get these 2 boxes, these 2 bigger boxes, and the 1 little box in this kit. All right, remember, you're only doing this if for some reason you can't pull new wire with additional conductors. Maybe they got fancy finished ceilings and you can't touch them or whatever it is. So the thermostat gets this little box put behind it. And what that guy does is it grabs a few of these wires from the thermostat and digitally combines them into 1 signal and sends them over some of the other wires. And then this other box right here is this guy right here. His job is to take those wires, and split them back into multiple wires. So I have 1, 2, 3, 4, 5, 6, 7 wires going in, 4 wires going out. It's digitally combined some of them into a communicating signal. And then this box's job is to separate them from 4 back into 7 again. So the thermostat thinks he's got 7 things connected. The indoor air handler thinks he's got 7 things connected, but really in the wall, there's only 4 wires run. And these 2 boxes are basically the sender box sends a little email to the indoor unit boxes. Hey, dude, I'd actually like second stage of cooling, please. Like, could you hook me up? And that guy's job is to then go ahead and turn that relay on. So the indoor air handler thinks this box is his thermostat. He has no idea it's not his thermostat. And the thermostat thinks this box is his indoor air handler. He has no idea that it's not. The second piece of that is this outdoor one that goes out at your heat pump outside on the roof. And what that does, same thing, this box takes some of those wires that we got the thermostat signal from and digitally combines them into a communicating signal. He basically sends an email. This is not actually email, I'm just using it as a concept. Sends an email to the outdoor unit that says, hey, I want this, this, or that to turn on. And they talk to each other. And this allows you to get that done. These boxes cost a couple $100. So usually you just run new wire, but sometimes you can't, and you'll need to do something like this. So when you're bidding a heat pump upgrade from a non-heat pump system, you may have to do additional electrical wiring, and you may have to do additional electrical low voltage wiring. So that should be included in your cost estimate when you're doing your payback calcs. Don't just say, oh, the heat pump cost whatever, $2,700 more than the AC replacement. Well, it's $2,700 more plus this extra wiring labor. So really maybe it's $3,500 more. You just got to include that math in your payback. Let's see if we have any questions typed in. We do have one from Mark. Do heat pump packaged units, rooftops, have substantially different weight than fossil fuel or resistance heated units that might present structural difficulties? No, they do not. In fact, you could possibly say that some units are slightly lighter. So if you took a gas-fired rooftop unit off and you put a heat pump version on, you are losing the weight of the gas-fired heat exchanger and the inducer motor on there. And you are gaining the weight of a reversing valve, which is like less than a pound, and electrical heating elements, which is also a couple pounds. So you're going slightly lower in weight, assuming you had everything else identical. You've got the exact same size and the same model and the same efficiency and everything. The heat pump would be slightly less than the fossil fuel version. Not enough to get excited about, but slightly less. The bigger challenge is usually when you're going from lower efficiency equipment in general, unrelated to heat pumps specifically, but lower efficiency to higher efficiency. One way to get more efficient historically has been to put in bigger condenser coils, which obviously weigh more. So that's been the challenge there from a weight perspective. There are other ways to get more efficient instead of getting a bigger condenser coil, because these manufacturers realize they're space constrained. They want to stay on that same curb. So one way they do it is by putting in variable speed condenser fans, multi-speed compressors, or even just 2-speed compressors, indoor variable speed blower fans, or 2-stage blower fans. These are ways we can get more efficient without needing more square footage of real estate for the condenser coil, and hence more weight. But generally, the heat pump version compared to the AC version would be the same or less weight. There would be nothing that would make it weigh more. All right, I think we're good on questions. There's more stuff. Type it in, man. And then if you have a complicated question, just type in, unmute me, and then I'll find you in the list and I'll unmute you and you can ask me your extra weird question. How are we doing on time? We're doing pretty good. One bad thing about not having dual screen today is I can't see where I'm at on the, we're doing really good on time. Okay. All right, let's go back to that. And I'll go back to that. Okay. All right, so electrical service might need to be upgraded for rooftops or air handlers to support electric heat. If it's an air handler, meaning it's a split system, an indoor and outdoor component, the outdoor unit probably doesn't need anything different from a wiring standpoint. It's the indoor unit where electric heater would be located that would probably need something different. If it's all electric, probably fine. If it's a fossil fuel conversion or a hydronic or steam conversion, then you would have to probably add electrical wiring to the indoor unit. Another option, which I mentioned last week a little bit, and we'll talk about it a little bit more this Friday as well, is a dual fuel system. Dual fuel means I have two fuel sources. So yeah, I'm gonna put a heat pump in. Great. It's the most efficient thing we can think of, right? It's the best efficiency thing we got. It's probably long-term the best for our environment, assuming that our power plants generate cleaner and cleaner power, electrical power plants. But it's hard to do, right? I have to add these electric heaters, or I have to add wiring for electric heaters. Electric heat is expensive to run compared to my gas heat. Now I'm trying to switch over to a heat pump, and it's going to cost me more to operate than my old crappy system. That's a tough sell for some people. Some places are going to do it because they just want to be better for the environment, and that's one of their company missions and goals, etc. Other places, they don't really care about the environment as much. That's just they don't care. That's not their main driving force. Their main driving force is their bottom line. And then the environment, yeah, if it makes kind of sense, I'll also care about the environment if it lines up with my bottom line. So that's where the dual fuel comes in nicely, because you can put a lot of hours on the heat pump, like we talked about last week. 80, 85, 90% of your heating run hours could go on the heat pump. And when it gets too cold and the heat pump can't keep up, right, because I size it for cooling, not for heating, then I turn it off and I switch over to the gas-fired system that I already own, right? So you could do that. It's easier to do that on a split system than on a rooftop unit. On a split system, I have the indoor component that already has either a gas-fired heat exchanger in it, duct furnace basically, or it has a hot water coil that's connected to a gas-fired boiler, right? So in those cases, I would leave the air handler alone. I would leave the boiler plant alone. I would just swap the outdoor unit to a heat pump version of that, and I would not change anything else. I shouldn't say that. I have to change the thermostat wiring. I need more wires. But I wouldn't have to change the high voltage wiring because I'm not adding electric resistance heat to the indoor unit. I'd just run my fan like normal off of that. So I can have a dual fuel split system with the outdoor unit being a heat pump and the indoor side having a hot water coil connected to a gas-fired boiler. And then I could do the math like we were doing a little bit earlier to figure out what that changeover point is on when I want to use the boilers to heat the building and when I want to use the heat pumps to heat the building. And it's not a big cost. I'm paying whatever the price difference is between an AC and the heat pump version of the exact same piece of equipment. And I'm paying for a little bit extra thermostat wiring. And I could have a dual fuel heat pump system with a hot water or steam air handler. If you have a gas-fired rooftop unit, this becomes more of a challenge because the gas-fired unit, packaged rooftop unit, you don't get a lot of choices on things. And I don't think anyone makes a gas-fired rooftop unit that also has a heat pump in it. For a while, we had one supplier that was doing it for 3, 4, and 5 tons only, but nothing bigger. And maybe there are still guys that do it like that. But if you have a rooftop unit, you don't have a lot of options here. If it's a split system, it's super easy. It's like almost a no-brainer to do a dual fuel system when you have a split system with a hot water boiler or steam boiler. But when you have a gas-fired and a gas-fired split system also, when you have a packaged rooftop, that's when it becomes unlikely that you're going to do the dual fuel system. And you're probably gonna have to pick a lane. Either you're gonna go all electric because that's the way your life is headed, or you're gonna stick with your gas furnace and not do the heat pump. Not that you could do it, I guess. You could get an outdoor mounted duct furnace, horizontal discharge rooftop unit, and connect it together like a Lego kit, an erector set. But it's probably not the best from an operational and service standpoint. Looks like another question popped up over on here. Gary asks, what determines when gas-fired unit comes on? Does thermostat or heat pump determine it? Thermostat. So we talked a little bit about this last week, and we didn't go all the way down the path, but we've click back on here. We go back to we'll go back to a normal thermostat. So let's say we have a split system, and the indoor air handler has gas heating with it, and the outdoor unit is cooling only, right? So we're more like this scenario on the left, I guess you would say. This thermostat needs to know the outdoor air temperature. So in the case of the ecobee, like I'm showing up in the corner, ecobee gets the outdoor air data from the internet, from zip code finder. So it looks and finds your current outdoor air temperature. The other option is you can get a thermostat like Honeywell or Venstar or somebody that has an outdoor air sensor that wires to the thermostat. So you'd have 2 more wires coming into the thermostat. There'd be more terminals on here, right? For outdoor air temperature. And now we go into an outdoor air temperature sensor outside. So one way or the other, the indoor thermostat needs to know the outdoor air temperature. And then we would use the type of math we did last week to find that economic and thermal balance points. Actually, last week we just did the thermal balance point, and I think this Friday we're going to do more on the economic. But you would look at the thermal and economic balance point. Thermal balance point, if you recall, is what outdoor temperature can my heat pump, for the way I chose to size it, not produce as much heat as I need from my building. And then the economic balance point means when is it based on the cost of my fuels, more cost effective to run my fossil fuel versus my heat pump system. And we're going to dive into that a little more deeply on Friday as well. So once I know that outdoor air temperature from my calculations, then my thermostat, I tell it that outdoor air temperature. And I think we had a screen that showed it last week. We'll tell it whatever that temperature is. Let's say it's 38 degrees, right, for this particular project. So at 38 degrees, the thermostat says, hey, if it's above 38 degrees, I'm running a heat pump, man. Let's go, heat pump time. And if it's below 38, I'm shutting the heat pump off and I'm running the gas furnace because that's the number you told me to switch it over at. So to give it that changeover point, some thermostats also have the ability to learn how long it's been taking to heat and cool your structure. And you can give it like a range. Say, hey, above this temperature, lock the furnace out so it can't run. And below this temperature, lock the heat pump out so it can't run. But in between these two numbers, I'm going to let you pick. I'm going to let the thermostat figure it out based on how long it's been taking me to heat and cool this building at those kind of temperatures in the past. So Ecobee can do stuff like that. So hopefully that kind of addresses Gary's question. So the answer to your question is thermostat determines when, based on the data you give it. The heat pump doesn't know anything at all. That's dumb. Jason says, what about costs associated with refrigerant line replacement costs for a split system, i.e. going from lower pressure R22 to higher pressure R410A or above, where the original joints are soldered and not braced? All right, if you're converting from one refrigerant to the other, you might be changing the piping system, but you would be doing that unrelated to the decision about a heat pump. If you were going to go from an old R22 cooling only system to a new R410A cooling system, you have to have the exact same considerations on whether you're going to change out the piping system or not, right? So having a heat pump doesn't change that answer at all, because all air conditioners, at least for the normal sizes, right, 3 through 50 tons, let's say, are all 410A right now, whether you want it or not, right? And then all heat pumps are R410A. So no matter what, you're going from 22 to 410A. So these decisions would happen unrelated to the heat pump decision. By the way, as a side note, we have a bunch of new refrigerants coming in our industry, but at the moment, 410A is what everything would be for all this normal size stuff. Does that make sense, Jason? So yes, you might have to do things to either replace the line set or clean the line set in some cases to get the oil and stuff out of it, but you have to do that anyway, unrelated to the heat pump decision. So when I look at the cost of changing someone to a heat pump, there's two ways to look at it. The way I always do it is, my AC is going to get replaced. I'm making that decision. I'm deciding on my AC, it's 18 years old. I've had this or that problem. I'm going to replace it. Now that I chose to replace it, what am I replacing it with? Another AC that's more efficient, or a heat pump? Which way do I want to go? And then I only look at the cost difference between replacing the basic AC and whatever it costs to do that, the cheapest quote I can get to get a new AC and its labor, versus the cost I can get on my other two choices, high efficiency AC or heat pump version of the AC. The other way you could look at it is, hey, I have a perfectly good air conditioner. I'm not getting rid of it. I put it in 7 years ago. I just want to know if it makes sense for me to replace it with something else. In that case, I would look at all the costs of doing the whole project as I do my economic payback calculation. Because my base choice is do nothing. Just leave my unit sitting there. Do absolutely nothing different. Just let it run and away I go. So how much would it cost me? In that case, it cost me the new heat pump or high efficiency AC, whatever it is, new heat pump, any changes to the line sets, any changes to the electrical, the labor of installing, everything's in. And it's a very expensive project at that point. But if I'm only looking at the delta between regular AC, new, and heat pump, then the delta is pretty small. So Gary, following up on our previous question, says we need a thermostat designed for heat pumps. Usually the answer to that is yes. There's some slight exceptions, but almost all the time you will need a heat pump thermostat. Specifically, you need one that has an OB output on it. What can I draw on here? OB output. Your existing thermostat might have that. It might not. Depends on what your existing stat is. If you have an Ecobee, it has that because all Ecobees do heat pumps, right? But not every thermostat you have on the wall does it. If you got an old stat from 20 years ago, it probably wasn't a heat pump if they didn't have a heat pump. You used to have to buy a thermostat that was specific for each application. Now you buy one thing and you program it for your application. So if they have a modern thermostat, let's say they replaced their thermostats 3 years ago, they probably have one that has a heat pump ability on it. If you're not sure, you pull it off the wall, you look for either on a modern thermostat, it would always say O/B. Old thermostats would have an O or B, two separate terminals. So you might need to replace the thermostat as part of the project, depending on what kind of thermostat you already have. Further on that, if you want to do the dual fuel thing, where you have the ability to run the heat pump or another heat source that's not electric resistance heat. So heat pump with a gas-fired furnace, heat pump with a hot water coil, heat pump with a steam coil. Any of those three examples, if you're doing one of those three, you need a thermostat that can support dual fuel. What does that mean? That means it has a way to know the outdoor air temperature, and it has a programmable set in there that you could say, hey, at this outdoor air temperature, flip me. You don't need a dual fuel thermostat if you are going to have a single fuel, i.e. all electric. So a heat pump with electric resistance heat needs a regular heat pump stat. And a dual fuel one, which is any kind of heat pump with anything other than electric resistance heat, needs a dual fuel heat pump thermostat. Mark asks, are there heat pump dedicated outside air systems that can be dropped in as replacements for gas-fired makeup air systems? There are heat pump dedicated outside air systems. They're probably not going to be ones that you'd be able to drop in. The amount of capacity that you would need for your market is pretty ridiculous, right? Dedicated outside air system, for those who don't know, is an air handling system that does 100% outdoor air. So instead of always having like 65, 70 degree entering air to the heat exchanger, it might have 0 degree entering air to the heat exchanger. So you need a lot of BTUs. So yes, you can get a heat pump that'll do that, but it's going to be, that system is going to be significantly physically larger than your existing system with gas heat. You're going to need a lot of coil surface area to do that. So that would not be a clean change out. That would be a throw everything I have in the trash, except my ductwork, buy everything new. It wouldn't be like one of these change outs we're talking about here. It would be much more involved. It's not too often that you would see dedicated outside air systems on older buildings. There's some exceptions to that. It's a newer idea where you've decoupled your outside air, fresh air conditioning from your indoor recirculation and conditioning. A normal air handler does both, right? We combine outside air and return air, and then we mix them, and then we heat and cool it. What you would do in this case is you have two systems. You have a dedicated outside air system. You typically have two systems. You have one system doing your straight cooling of the space. So it might be VRF, ductless mini splits, chilled beams, little tiny fan coil, something like that. And then you have a dedicated outside air system that's treating all the fresh air coming in. So that is not typically found on older buildings. The exception to that might be what we call a makeup air unit, which you might find like on apartment buildings where they used to bring fresh air into the hallway, the makeup of the apartment building, and dump it into the hallways and let it leak under the doors into your individual apartments and condos and stuff. And those often were typically gas-fired units, although sometimes they were electric, but they were typically gas-fired units. We didn't call them dedicated outside air units because they didn't have cooling function typically. We call them makeup air units, but it was kind of the same idea. So yeah, you're not going to have as many heat pump options for dedicated outside unit. There are options, but you're going to need to either grossly oversize it to get enough heat, like grossly oversize it, or do something else to help it. One of the things you might be choosing to do to help it is energy recovery, which is a whole nother class in itself. It's a whole nother hour-and-a-half thing to do someday with you guys. Energy recovery would mean I'm going to take energy, in this example, heat energy out of my exhaust air that I'm going to exhaust out of the building, right? I'm sending it out the bath fans or whatever it is. I'm exhausting this air out, but instead of letting the air just leave, I put a heat exchanger in the exhaust air and recover that heat. And then I have that heat be piped over to the incoming ventilation air for the dedicated outside air unit and use that to preheat my outside air. From a code standpoint in your state on a new system, for most applications, energy recovery would be required for dedicated outside air. There are some exceptions where you don't have to do it, but for most of them, you would have to do it if you're installing a new system. So the energy recovery would preheat that outside air, so it wouldn't be as extreme. Thereby, a heat pump version of the dedicated outside air unit might be able to keep up a little bit better because the energy recovery unit is taking the brunt of the load. I think we're caught up on questions. If there's more stuff, ask. I think we got them all. I don't see any new ones yet. Okay, so let me hide this. Let me figure out how to get my mouse control back. Okay. Where were we at? We already did that stuff. Okay. Oops. Discard my notes. Okay, my last slide. We already did the utility rebate discussion last week, so I won't repeat that with you guys. All right. So the metrics associated with all this type of equipment. So AHRI, if you didn't know, is the American Heating Refrigeration Institute. It is a organization that was the merger of the old ARI, which is American Refrigeration Institute, and Gamma, which was the heating folks. They merged together. They're basically doing similar things for heating and cooling. And they were like, why don't we just kind of do it together, right? So it's a merger like 20 years ago. So you might see ARI mentioned once in a while. That's just because whoever did it is old school and they keep forgetting to put the H in there. But in other cases, AHRI. So they establish, I should say first of all who they is. They is a collection of industry stakeholders. So it's a lot of the manufacturers' equipment. It's a lot of people from ASHRAE. It's people from building owners, code inspectors. There's a lot of people that are involved that could be on these various committees. But in large part, it is driven by manufacturers because they're the ones that are actually making the stuff that's getting tested for AHRI standards. So they write all the standards and how things get tested. And it's a peer review process like many other standards, meaning that I propose to write the standard this way. We sit down at a meeting and 3 other guys are like, dude, that's stupid. We're not doing it that way. We need to do it this way. And we all discuss it until we all agree. And if we can't agree, then eventually we just vote on it and say, okay, majority rules, man. Sorry, bro. So it's not like one manufacturer is dictating it. They're all basically agreeing that this is how things should be tested. So they set the standards on how things are tested, what temperatures you have to use, what conditions you have to use, how big the lab's going to be, all these different things they set. And from our perspective, the unfortunate part is none of those tests line up with my life. My life is this building, or it's that building, or it's this house, or whatever it is. And now I got to use this test data. It is what it is, right? So these numbers don't do a great job of telling me what's going to happen in my building. What they do a great job is telling me if I have 2 pieces of equipment that are the same type of equipment from manufacturer A and manufacturer B, how efficient is each one compared to each other, right? They do not do a good job of me comparing disparate types of systems. So if I want to compare a gas furnace to a heat pump, this is not going to help me very much at all because there's no real conversion between those things. I'll have to do an energy model or use one of those cheating tools that I used yesterday or earlier today and do a model that way. If I want to compare heat pump A to heat pump B, this is fantastic. If I want to compare air conditioner A to air conditioner B, this is fantastic. If I want to compare air conditioner and furnace combo to heat pump, this doesn't do me any good. But the software that I'm going to use to energy model those examples is going to want this AHRI data from the equipment as its inputs to figure that out. So for starters, for the kinds of equipment we're talking about today, which was commercial packaged rooftops and commercial DX split systems, there's this magical dividing line of 65,000 BTUs of cooling. If it's less than 65,000 BTUs of cooling, the equipment gets tested as if it was a residential application, and they use the residential testing metrics. And if it's above 65,000, 5 tons of cooling and above, they do the commercial testing and the commercial metrics. However, residential small systems get put into commercial buildings all the time. It's a daily thing. It's constantly happening, right? The classroom right next to me has a 3-ton rooftop on it, cool in the classroom. It's a residential system that's only used in commercial buildings, but it's under 5.4 tons, so it's a residential system. All right, so terms you are probably familiar with. You probably heard the term SEER. SEER only applies to 5 tons and less. Above 5 tons, there's no such thing as SEER. It doesn't exist. Never heard of it, right? SEER is my cooling efficiency. It stands for Seasonal Energy Efficiency Ratio, and it's for cooling. It has nothing to do with heating in any way. If I happen to have a heat pump, it would have a SEER rating for cooling and it would have an HSPF, heating seasonal performance factor, for the heat mode. Same piece of equipment, run through two different tests, one with the reversing valve set for cooling, one with the reversing valve set for heating. I should point out that now we don't use SEER and HSPF. Now we use SEER 2 and HSPF 2. I believe we briefly talked about this on Friday. The old testing standard was changed for the static pressure in the ductwork that we have to test all this stuff at. So now there's a new standard. So SEER 2 and HSPF 2. You will also see EER or EER2 for all that size equipment, right? EER2 being the new one. That's the full load efficiency. It tells you how efficient this thing's going to be if you ran at maximum capacity and locked it in and let it roll there. That's not a real life scenario, so hardly anybody pays attention to that anymore. But it used to be the only metric we had. Now that we have things like SEER in the past 30, 40 years and HSPF2, we don't really care about ER, but it's there for old people. By old people, I don't mean old customers. I mean old people that make these rules. All right, so those guys are for how I test my cooling and my heating on these smaller systems. AFUE, annual fuel utilization efficiency, is for gas heating, either a gas furnace or a gas boiler, right? How efficient are those guys? So a regular cooling system, you'd have a SEER, or nowadays a SEER 2, an EER2, and an AFUE. If it was a heat pump, you'd have a SEER 2, an EER2, and HSPF2. If it was a dual fuel system, you'd have a SEER 2, an EER2, an HSPF2, and an AFUE. All those different metrics that representing how efficient each of those pieces are. Once you get to bigger stuff, 5 tons and larger, or 5.5 tons and larger, excuse me, then you don't get any of that terminology. There is no SEER or HSPF. We still have EER, which means run at maximum full. There's no ER2. We're still on regular EER there. Nothing's changed on their testing standard. And we have IEER, Integrated Energy Efficiency Ratio. That is a part load version. It's basically SEER for commercial stuff. This is a significantly more important number than full load because you're almost never at full load. So I don't care. I don't care if this thing's a dog when it's 95 degrees outside. I want to know how efficient it's going to be at 90, 89, 91, 87. That's more important to me than 95 because 95 hardly ever happens. That's where the IEER comes in. What they do for IEER is they test it at 25, 50, 75, and 100% loaded. 100% means it's the regular ER. They load the machine in that way with those kind of conditions, and then they put a weighted average on there, significantly weighting the middle too, and barely putting any weight on the other ones. Like 2% of it goes on here. I want to say 12% of it goes on here, and everything else goes on the middle too. So basically, it's a way to see how efficient it is in part load. A lot of utility rebates, and in some cases even municipal codes now only look at IER and not ER. Department of Energy commercially needs to stop using this completely. They have no specs for minimum ER anymore. They don't care. It's not their problem. They only care about the part load. So that's for all your cooling systems. For heating, we have thermal efficiency. It is a percent, just like AFUE. AFUE, you might have a 95% efficient furnace. I'm realizing this slide is becoming a sloppy mess right now. And then for your packaged equipment with gas heating, maybe you have an 82% efficient rooftop unit or something like that. For packaged rooftop units, it's going to be really hard to find anything above 84% efficient. There are a couple units out there, but the challenge is once you get above like 86% efficient, you start condensing in the flue gases, which means the condensate line. Well, a condensate line on a roof outside in the winter in places where it gets below 32 degrees is an issue. It freezes, and that becomes a problem. So you either have to run the condensate line down through the inside of the building instead of dumping it on the roof like normal, or you got to put like heat trace tape on the condensate line and spend electricity so it doesn't freeze, which is kind of stupid. I'm going to swap electricity for efficiency. So most of the time you won't see rooftops above like 84% efficient. There's a couple specialty models, but in general, that's about the cap. If you have a heat pump, you don't get an HSPF number. You get COP, coefficient of performance, at 47 and at 17 degrees. And we talked about those a little bit last week too. But basically, they run it on a 47-degree day, see how efficient it is. Run it on a 17-degree day, see how efficient it is. By the way, I didn't mention it, but residential heat pumps now, in addition to HSPF, they now also have a COP5, which means coefficient of performance on a 5-degree day for the small ones. So it's kind of weird. All right, I have 1 minute left. What did we not cover that we need to cover? See if there's any questions pending. I think we got all the pending questions. This is what we're going to pick up with on Friday. Friday, we will be meeting in the morning, Friday mornings, Monday afternoons, Friday morning, and it'll be at, let me forget the time. Let me remember the time. Let me forget the time. It sounds bad. 9:30 Eastern time is when we'll meet on Friday. And this is the topics we're going to cover. We're going to dive more into these residential split systems when they're used in commercial applications. We'll do PTACs like we do at hotels, ductless mini splits, which I'm sure you probably heard of. And then we'll do pretty detailed discussion on how variable refrigerant flow stuff works. Because if you didn't know it, every VR system used in the United States is a heat pump. Any other pending questions? All right, well, thank you guys. And I'll stay on for like another minute or two in case somebody does have a question. Otherwise, I'll stop the recording and we'll move on. Thank you guys. All right, a couple questions that did pop up. Dan asked about a software tool for BOSNG. So I'm assuming Boston Natural Gas versus heat pump comparison. All right, I'll make a note. I'll send you guys link to be able to download all that software and instructions on how to install it. It's pretty convoluted, but I can do that. We call that software Invest. So I'll send that to you guys. What else? Gary asked if we've done heat pumps for Chicago area with gas boilers. Yep, we've done that several times. There's lots of ways to do that. One of the common ways that comes up a lot is we have a lot of buildings that are like rehab products, like a loft building in downtown Chicago, for example. You know, the building's been sitting there for a couple of years. Some developer gets it, they gut it, they decide, you know, you turn it into offices and whatnot, and the building has, steam radiators or hot water baseboard or whatever, and doesn't really have a cooling system. So we'll add cooling to those systems, like VRF, and then we'll keep the radiators or the baseboard or whatever they have as our dual fuel secondary source. So that's happened a lot. We have not had a lot of situations where you've had air handlers that already have cooling and gas-fired heat be converted over to heat pump versions. It's usually buildings where we're adding cooling for the first time. But there's been both. That's been the more likely scenario. Dan sent his email. Let me see if I can copy it. Okay. Any other questions? Discard those notes. Okay. All right. So I think we got everybody answered, and I'll see you guys on Friday. Thank you.